Continuing with section 3.5, let's move to example 2, which is an illustration of the conjugate pairs theorem. Write a polynomial function with real coefficients of lowest degree possible with 3 and 3i as zeros. So notice we want our function to have real coefficients and we want its degree to be as small as possible. So we want to only deal with as many zeros as are really necessary. Now, to obtain real coefficients, if we notice that we have a non-real number as a zero, then by the conjugate pairs theorem, its conjugate has to be a zero as well. So, since 3i is a zero, so is its conjugate minus 3i. So the non-real zeros must occur as conjugate pairs. So that takes care of the non-real zero. What about the real zero, 3? Well, the conjugate pairs theorem does not apply to real number zeros. So if you see that 3 is a zero, you don't have to conclude that, say, negative 3 is also a zero, because 3 and negative 3 are opposites, but they're not conjugates. In fact, the conjugate of a real number is the same number, the number itself. In other words, 3 is its own conjugate as a complex number. So it's only the non-real numbers where we have to concern ourselves with finding conjugates. So we actually then have 3 zeros, which would suggest that the function that we want to find would have degree 3. Since we know the zeros, we can write the factors using the factor theorem. Let's call our function f of x. We know 3 is a zero, so that means x minus 3 is a factor. We know 3i is a zero, so by the factor theorem that means x minus 3i is a factor. And we know negative 3i is a zero, so that means by the factor theorem x minus 3i, that is x plus 3i, is also a factor. So basically that's our polynomial in its factored form. If we want to write it in the more traditional expanded form, the easiest way to do that is to multiply the two factors involving the imaginary numbers together first, just by FOIL. So I'll leave x minus 3 out in front. By FOIL, we would get x squared. Outer term would be plus 3ix. Inner term would be minus 3ix. And the last term would be negative 3i times 3i, which would be minus 9i squared. Now notice that the terms in the middle cancel each other out. Now what about minus 9i squared? Is that an imaginary number? Well, it's actually not. It turns out that if I is the square root of negative 1, then I squared would just be the real number negative 1. So minus 9i squared is really minus 9 times minus 1, or positive 9. In other words, minus 9i squared is the real number, positive 9. So we can simplify this to x minus 3 times x squared plus 9. Minus 9i squared is plus 9. Then we can use FOIL a second time to write the final expanded form of f. x times x squared is x cubed. Then let's do the inner product next. Minus 3x squared. Then the outer terms, plus 9x. Then the last terms, minus 3 times 9, minus 27. So as you see, the polynomial that we need that satisfies the conditions given in the problem is a third degree polynomial, and indeed it does have real number coefficients. Example 3 illustrates another application of the conjugate pairs theorem. Given that I times the square root of 3 is a 0 of f of x equals, and you see x to the fourth plus, etc., find the other zeros of f. Now, I times the square root of 3 is an imaginary number. The coefficients of f, 1, 1, 2, 3, and negative 3, are all real numbers. So by the conjugate pairs theorem, if this non-real number that's given is a 0, then its conjugate should be a 0 as well. So, since I square root of 3 is a 0 of f, so is its conjugate, and the conjugate would be minus I square root of 3. So the non-real zeros must occur in conjugate pairs. Okay, so then how do we find the other zeros? Well, one approach would be to use synthetic division, using I square root of 3 and minus I square root of 3, and doing a couple of synthetic divisions to obtain a quadratic factor. However, synthetic division with imaginary numbers is not particularly convenient or easy, so I'm going to take a different approach, and that approach is as follows. Since we have two zeros of f, we have two factors, and those factors would be x minus I square root of 3 and x plus I square root of 3. This just comes from the factor theorem. If c is a 0, then x minus c is a factor. Now, if we multiply these two factors together by FOIL, we get x squared plus, I'm going to write I square root of 3 times x. Then for the inner product, minus I square root of 3x. And then for the product of the last terms, it would be minus I squared, and the square root of 3 times the square root of 3 is the square root of 9, which is just 3. Now, notice the middle terms, as in the previous example, cancel, and I squared is negative 1. So the last term is actually plus 3. In other words, when we multiply these factors together, we get a fairly simple factor, x squared plus 3. So we can say x squared plus 3 is a factor of f. And if x squared plus 3 is a factor, it should divide into f evenly. Now, we can't use synthetic division to divide f by x squared plus 3 because x squared plus 3 is a quadratic factor, and synthetic division has to be done using only linear factors, first degree factors. However, we could use long division, which we studied at the beginning of the chapter, and that should allow us to divide x squared plus 3 into f and determine the remaining factor, factor or factors that would give us the other zeros of f. So let's give that a try. I'm going to take x squared plus 3. I'm going to divide that into x to the fourth plus x cubed plus 2x squared plus 3x minus 3. Now, the nice thing about this, if you want to think that there's anything nice about it, it probably doesn't look very nice. The nice thing is that given the conditions stated in the problem, we're guaranteed that this is going to divide in evenly. So we should be expecting a remainder of 0, and it shouldn't be actually too hard to do the division with that in mind. Okay, to get x to the fourth, you would need x squared as the first term in the quotient, and then you're going to multiply x squared times x squared is x to the fourth. X squared times 3 is 3x squared, and I'd put that below the 2x squared term. Remember, with long division you subtract, so the x to the fourths cancel. 2x squared minus 3x squared is minus 1x squared. The x cubed has to come down from the previous step, and then I'll just go ahead and bring down the 3x as well. Okay, the next term we would need would be an x. X times x squared gives us x cubed. X times 3 gives us 3x. If we subtract, the x cubes cancel, the minus 1x squared comes down, the 3x's cancel, and then we can bring down the minus 3. And then one more step, now use minus 1. Minus 1 times x squared is minus 1x squared. Minus 1 times 3 is minus 3. Subtract, or add the opposite if you prefer. Remainder is 0 as expected. So what we have done is we have obtained a factored form of f as the product of x squared plus 3, which of course came from our two imaginary zeros, and then the complex conjugate zeros, that is. And then from the quotient, from the division process, that's the other factor, x squared plus x minus 1. Now any remaining zeros would need to come from that factor. Now that's a quadratic factor. So if we solve it as a quadratic equation by the quadratic formula, minus b plus or minus the square root of b squared minus 4ac over 2a, with a equal to 1, b equal to 1, and c equal to negative 1. Then we should be able to find the remaining zeros. And by the way, x squared plus x minus 1 does not factor, so that's why I'm using the quadratic formula here. Okay, substituting in to the formula, it's minus 1 plus or minus square root, b squared is 1, minus 4, a times c is negative 1, all under the square root, and then the whole thing divided by 2 times a, which is 2 times 1 or 2. Simplifying a bit, it's minus 1 plus or minus, it's 1 plus 4 under the square root, so that's the square root of 5 over 2. So we can conclude that the remaining zeros are the conjugate. We were given I times the square root of 3, so the conjugate minus I times the square root of 3, and then two additional real number zeros, minus 1 plus the square root of 5 over 2, and minus 1 minus the square root of 5 over 2. The first of those is approximately 0.618. The second one is approximately negative 1.618. Those are both real numbers, but irrational numbers. So those are the remaining zeros of f.